that I'm being very clear, right? And this is a tough lecture. Now, I'm going to take the liberty of being slow and maybe going over. Some of this lecture is not going to be covered by me. It's actually going to be covered by the first recitation after the break, which will be on Monday and actually substitutes for the class. So this is, I'm doing this because we are releasing the homework this week. And we need you guys to be familiar with the ideas, but then the details of exactly how you implement it, we think you're smart enough to not require the recitation. But so the recitation is going to be more of an assistance than a mandatory watching to attempt the homework, because the slides are sufficiently self-explanatory if you actually watch the video lecture and then go through the slides on your own, especially the portions I've skipped, spend some time on it, then it should be reasonably clear how to solve these problems. Okay. Now, one of the things we will be putting up this week is a little handout on how to compute derivatives. And I expect you guys to go over that handout and maybe ask questions on Piazza, because we literally give you instructions on how to write your own autodiff. So when you're done with this little assignment, you should, or this, if you just follow the instructions on the handout, you should be able to write your own autodiff, right? So for now, we're going to continue with the problem of sequence-to-sequence models. Which was the last topic we addressed. We sort of began discussing this issue at the end of the class, and for the next couple of lectures, we're going to sort of go over this topic and in depth. So here's the basic problem. You have some sequence x1 through xn going in. You have a different sequence y1 through ym coming out. So observe the difference in the indices. The number of symbols going in, n, is different from the number of symbols coming out, m. This means that there is no one-to-one correspondence between the number of symbols in the input and the number of symbols in the output. So in other words, you cannot assume any kind of synchrony between the input and the output. So we have various problems of which answer to this kind of model, right? Which require this kind of model. Speech recognition. Speech goes in, the transcription comes out. Your speech may be 5 seconds long, the transcription is going to be 15 words. Machine translation. A typical sentence in written English would be 30 words, and someone writes it in Chinese and it's probably 3 characters, right? So I've actually seen that it was hilarious. We have these dubbed movies. I was watching a English movie dubbed in Spanish, Portuguese, and Chinese. And so the person would speak on for like 15 seconds. The Spanish translation would scroll over 2 times or 3 times. It'd be much longer than the English, and there'd be 2 characters in Chinese. So it's very efficient coding. Anyways, so the point being, there is really no one-to-one correspondence between the length of the input and that of the output. Similar thing with question answering systems or dialogue systems. Somebody states something, the machine must respond. The length of the response is not directly related to the length of the query. So you can sort of see 2 distinct formalisms over here. The first is something like speech recognition. In speech recognition, you have the speech going in, you have symbols coming out. The speech may be 48,000 or 120,000 samples of speech. Out comes 6 words. There is no one-to-one time correspondence, but there is an order correspondence. Meaning if I basically the portion of the speech that corresponds to I precedes the portion of the speech that corresponds to 8 in this case. So there is an order correspondence. You can have other problems like machine translation. So I ate an apple, ich habe einen Apfel gegessen. It just translates English to German. And if you try to look at the correspondence there, again, the 2 are not the same length, but I becomes ich, 8 actually becomes 2 words, habe gegessen, and they split across the sentence. And apple, again, these things cross over, right? So Anne is here, Apfel is here. What you observe is that the output order is not the same as the input order. So there isn't even an order correspondence. For today's lecture and the next recitation, we're going to be going over case 1, where we assume that you have order synchrony. So the input and the output have an order correspondence, like in speech recognition. So again, this is an order synchronous process, but it's not necessarily time synchronous, which means that the number of outputs is not the same as the number of inputs, but then you do have a notion of a correspondence. So here is the key piece, right? I have this is something that we're going to keep coming back with. I have, let's say, these are my speech vectors. We've been dealing with speech. You have a sequence of spectral vectors. And then the actual sentence is, hello world, right? So you know exactly where the word hello ended. So this is where hello happened, right? And you could say this is where the word world happened. So you actually have a notion of time in the transcription text. It's just that the output doesn't need to come out at each time instant. The specific time at which you produce a symbol can change with the symbol and from instance to instance, right? So this is the kind of model that's you're going to build on. This model we've seen already. This is the simplest instance of such a problem, where maybe I'm trying to recognize phonemes or words. So you listen to the entire word, and then when the word is done, you produce an output symbol, right? So this is, and here is the extension of it. You listen to the input, and every now and then you produce an output, but we don't know a priori exactly where the output must be produced. So the basic model, of course, is this guy here, right? You have a sequence of inputs, and at the end of the sequence of inputs, you produce an output. Say you see some speech, you say this is the phoneme ah. And when we train such a model, there's only one place where you get a cue about what the error was. And the one location at which you get the cue was at the instant at which you produce the output. So you will have an output at this time. You have a target output at the same time. You can compute the divergence between the two. That divergence can be back propagated across the net to compute derivatives with respect to all the parameters of the network. Now, this simple or simplistic mechanism ignores something important, which is that it ignores what happens at the intermediate times where there is no output assigned. The fact of the matter is that the network actually produces an output at every time. What we are doing is to ignore all outputs till the very, very final time instant. So we can try to exploit the information in these locations, these time instants, and the way we would do it is to pretend that the target output at these times too was the same as the final output. So although in principle we want the output ah only to be emitted when the entire input has been processed, for the purpose of training, we're going to assume that the sound was always ah, which is true in this particular case, right? If I'm just going ah, it doesn't matter where you stop, the sound is ah, right? So I'm going to assign the same symbol to every one of these outputs. And now I can compute a derivative. I can compute a divergence over two sequences, which is, again, for this particular setting, we are going to assume that the total divergence is the sum of the divergences at individual times. And so I can compute this, or a weighted sum of the divergences at individual times. And this I can use. Now, the typical weighting actually depends on the problem. For speech, you can assume that the weights are all 1. For something like question answering, where you really need to see the final word before answering the question, you might want to make the weights much higher towards the end than at the beginning. Maybe the initial weights are all 0 and the final weight is 1. And this is the divergence that you're going to differentiate to compute the derivatives, right? So we're going to focus in this lecture on the instance where it's reasonable to assume that all weights are the same, that even though I'm actually creating this artificial sequence where I just took the final symbol and repeated it many times, right? I'm going to assume that in reality they're all valid and that all of them must have a weight of 1. So this is the assumption I'm going to make. In other words, we're going to assume that these weights are 1. Everybody clear with what I'm doing over here, right? So you see the difference between what has been given and what we are assuming. And this is important. So now here's the more complex problem. Now this is something this is going to be the focus of this lecture. So you're given a sequence of inputs, and you must asynchronously produce outputs, meaning you're processing the inputs, and every now and then you're going to produce an output, right? So the model itself is a simple concatenation of the simpler model we saw here, right? This is just a concatenation of many copies of this model. But because we do not know how many time steps one must process before you produce the next symbol, this simple concatenation complicates issues. Now, and the reason for this is that the network itself actually produces an output at every time. We have to decide which of these outputs to pick to get the correct output sequence. And this information, the information about when to read the output, has not been provided to you. And this makes it hard, right? Because the network has produced an entire sequence of blue boxes. Somehow we must figure out that the boxes to read are this guy and this guy and this guy and this guy, right? And this is a challenge. So now let's see what the problem that we are really facing is. Okay. Now I'm going to assume, where did I put my chalk? Yeah. So let's consider, I'm just going to use the symbols A, B, C, and the alphabet in the abstract for now. So I have a sequence of inputs, x1, x2, x3, x4, x5, to whatever length, right? The sequence is some length t, and I must produce output of sequence A, B, C, let's say A, B, C. I do not know exactly how many symbols I must produce, right? Because when you consider the example of speech, somebody speaks, you don't know beforehand how many words were spoken. Determining how many words were spoken is part of the problem, right? So now that means that we really need to what we really want to do is to find the word sequence or the symbol sequence that best matches the input. We are going to think about it in terms of probabilities. Now, consider what the network actually produces. If you're using a softmax output, as we know, the network actually produces a probability distribution over all possible symbols. So if we were doing phoneme recognition, these might be your phonemes. But by the way, for those of you who came in late, today is a holiday lecture, which means I'm actually going to go over. And just, if I think I'm going to take too long, I'll give you a 5-minute break somewhere in the middle so you can go wash your faces. I know you're sleepy. And then you come back in and continue to get tortured. Okay, here's what you output, right? At each time, you're outputting a vector of probabilities, and over all of the symbols. Now, you're producing a vector of probabilities over all of the symbols at every time, at any given time. What is this vector? This is the probability. This is the set of probabilities for all of these symbols at time 3 after having considered all of the inputs from 0 to 3, right? You've processed all of them and then produced the probability vector. So in other words, this is the a posteriori probability distribution. The probability assigned to the symbols conditioned on all of the inputs until that time, right? So for example, if I were to look at, say, y4d, which is the number over here, this is the a posteriori probability that the symbol, the phoneme at time instant 4 was D, given that the inputs were x0 through x4. Does that make sense to you? Right? You're computing a posteriori probabilities. What is the actual process that we're trying to do? When I'm trying to hypothesize the complete symbol sequence, in this case, I would be hypothesizing a complete sequence, symbol sequence A1, ABC, or more generically, let me write that as S1, S2 through Sk. Right? In the specific example, case 3, S1 was A, S2 is B, S3 is C, right? And what I am trying to find is the symbol sequence that is most probable given the entire input. So you're seeing the entire input, find the most likely symbol sequence. That is the actual question that we are trying to address. Make sense to everyone? Right? Now, when we make this statement, what are we not worrying about? We are not worrying about when the symbols were emitted. The only question I'm answering is, what is the most likely symbol sequence? Given the input, I'm not interested in when the symbols were actually emitted. Okay? So, do you see the difference? So, as far as we are concerned, this one, A, B, C, is the same as A, B, C. Shifting the symbols around doesn't really matter to us. We are only worried about the symbol sequence itself, not the location. Okay? So this is the problem we are trying to address. The issue is that that information is not hidden over, is not immediately apparent from here. So we're going to make an approximation. The first approximation I can make is to say, find me, so this is the order synchronous symbol sequence, but it's not time synchronous, right? The number of outputs is different from the number of inputs. So I'm going to consider two variants over here. Now this is key, okay? So something like S1, S2, S3, so which might be say ABC, right? This I will call my order synchronous output, okay? Which just tells me how many symbols there, what symbols there are, but it doesn't tell me when the symbols occur, okay? And then if I have all of my inputs, xt, then if I say that A occurs here, B occurs here, and C occurs here, remember the extension I made, right? So what this really states is that this entire segment represents A, correct? If I give you the time instant, it says this portion corresponded to the symbol A, and this portion corresponded to the symbol B, right? And this portion corresponded to the symbol C. So when I find out exactly at what instance the output occurred, then I'm going to call this an alignment of the symbol sequence against the input. Right? I've aligned the symbol sequence and told you exactly at what times each of these symbols occurred. So you see the difference between the symbol sequence itself and the alignment of the symbol sequence. Any questions? Right, okay. So alternately, I can imagine that this guy is what I'm trying to produce, right? So the alignment of my symbol sequence is going to be something of this kind, which consists of repetitions of the symbol for as long as the symbol is valid, right? And then the symbol changes, and it's going to be repetitions of the next symbol for as long as the symbol is valid, and so on. Yes?
What if we have consecutive outputs of the same type? For example,
we will get to that later in the class. Yes, Kiran? Same question? Okay. Because you're absolutely right, right? The alignment of the two is going to be the same in this case. Okay? Now you observe the difference. You notice the difference between the alignment and the symbol sequence itself. The symbol sequence itself says this is just ABC. The alignment says A occurred from here to here, B occurred from here to here, and C occurred from here to here. Okay? What we would like to do is to produce the symbol sequence that is most probable. Right? This is hard. We'll see how we can actually do it later in class. Instead, what we can do is to produce the aligned symbol sequence, which is most likely. Now, the difference between the aligned symbol sequence and the raw symbol sequence is here the raw symbol sequence is ABC. The aligned symbol sequence includes all of these repetitions. Right? And so I'm going to try to find the aligned symbol sequence that is most likely. Now, this is key. This distinction is what we're going to build everything on. So if you don't get this, stop me right here. Right? Questions?
So the output of where you have the last A, is that input also corresponds to A, or does that correspond?
That corresponds to A, right? Because the input went in and the A came out, right? Yeah.
So
Yeah.
there is like a one-to-one correspondence.
Yeah. So we've taken this thing that didn't have a one-to-one correspondence and expanded it to something that did. And the expanded version is the aligned version of the input. You have literally aligned it in time to the input. Okay? So, do I see any puzzled faces? No, because it's going to get very puzzling very fast. Now, this I can find. I can find the aligned sequence very easily. How do I do so? I can guess it. I can just pick the most likely symbol at each time, right? If I pick the most likely symbol at each time, that's going to give me a sequence of symbols, which is going to look a whole lot like this. Right? And from this guy, how do I collapse it to ABC? I just pick the last guy in each time, right? And that gives me the ABC. Make sense? Yeah.
So at the beginning of each, I guess, like the beginning of G, for example, is it likely that we'll have like a high probability of error just because we haven't seen very much of G yet?
So this is not the probability of error, right? This is the probability of the symbol itself.
Yeah, but I guess is there like a high probability that like the symbol will be like misclassified just because of that?
Because you haven't seen enough evidence. You're right, right? Yeah. I mean, if you decided that this is the output, right? I mean, again, defining error is kind of, you're right in principle, but as we'll see, defining the error is kind of hard. The problem with this lack of synchrony is that it really makes things very painful, right? Hard to define, okay? So what is the issue with, so here's what you're suggesting, that I can merge everything, all repetitions, and just put the symbol at the end of the repetition, right? So from an alignment to a symbol sequence, which is to say from a time synchronous sequence to the compressed order synchronous sequence, all I need to do is to merge repetitions. And this, of course, leads to this problem that you guys mentioned. How do I distinguish between repetitions in the compressed sequence and just unique verse instances? So I cannot distinguish between FF and a single F, right? It's an issue we'll deal with later. And if you just did this, what you might get is often going to be meaningless, right? So you can try to get around this by having external constraints, like, I'm only going to allow things in a dictionary, blah, blah, blah. There are ways of getting around it, but what we will do in the rest of the class is to figure out later in the class is to see how we can actually do this as part of the model, okay? Anyway, we will refer to the output process of obtaining the output from the network as decoding. So getting this time synchronous or the order synchronous output from the network is what we will call decoding, okay? So observe that when I do this, right, what I produced was an order synchronous, a time synchronous output. I produced the most likely time synchronous output. This is not necessarily the most likely order synchronous output. Why would that be? Anybody want to guess? You, of course, must guess, right? You know this answer. So consider this. Does somebody want to come here and stand on the rope for me? So it doesn't go back up. Now, look at this, right? I can get A, B, 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 C, C, right? And this represents this. Which order synchronous output does this represent? This is just ABC, correct? And this can have, let's say, the probability of 0.5. It's quite high, right? And then I might have the other versions, A, B, 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 C, C, A, B, B, C, C, then, you know, A, B, 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 C, C, C. And you can have all of these other variants which give me the same order synchronous output but different time synchronous outputs, right? And just giving you a completely hypothetical case where each of these, for whatever reason, has a probability of 0.0000001, okay? That means across all of these combinations, the total probability is maybe something like 0.5. I might have a different output sequence, which could be C, 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 D, E, E, and then C, D, D. And this was 0.4, and this was 0.4. Okay, the numbers have to be normalized, right? Each of these individually lost out to ABC. But if you considered across all variants of CDE, the sum here was 0.8, here the sum was close to 0.5. Right? So which of the two would you actually choose? Which was the more likely order synchronous sequence here? CDE, right? Because across all possibilities of alignment, this actually ended up having a higher probability. So while ABC was the more likely synchronized, time synchronous output, CDE was the more likely order synchronous output. And what we are really trying to find is the more likely order synchronous output, not the most likely time synchronous output. Question here? Make sense? Yeah. So this is suboptimal. But let's say assume that we can live with it, right? So if I'm going to live with it, I'm going to assume that we now know when to output symbols. Problem solved. Not really. We'll get back to this, okay? But for now, let's focus on how do I train models. Now, simple enough. If somebody gave me in my training data, the training data is different from testing, right? In my training data, if somebody actually gave me the exact instance at which the output occurred, then training is easy, right? All I'd have to do is to compute the divergences at these locations, and then I can pass these divergences backwards, the derivatives of these divergences backwards, and then I can train the model, learn the parameters, right? Or I can do the simpler thing. This is the order synchronous output. I can create the aligned version of it, which is going to insert repetitions like so, right? Which is the time synchronous aligned version of the output. And now I'm using all of the remaining symbols as well. And now I can compute the divergence over the entire lot and pass the derivatives with respect to the divergence backward, right? And train my model. So this is also easy, yeah.
So if, let's say your first pass, you get a different number of outputs than there is in the desired output, how do you make that comparison?
So where is the first pass?
Where is the first pass?
Yeah, this is the training data, right?
Yeah.
Okay.
Right.
We'll get to that.
Okay.
I think I understand your question, and we have the answer, right? Now, here is something very important that I want you to note, right? What are we doing? We are summing the divergences at every time instant. I'm using one-hot representations for the target symbol, right? So if I'm using one-hot representations for the target symbol, what is the divergence at any time? The cross entropy loss. The cross entropy loss is simply minus summation target log output, right? The target is 0 for all but one symbol. It's 1 for the one remaining valid symbol, right? So the way we would write it, if you have all of these symbols, so if you have symbols S1 through Sn, okay? C1 through Cn, so we don't confuse this. You're going to get outputs O1 through On. The network is going to produce probabilities for all of these guys at each time. Your one-hot representation is going to be a bunch of zeros and a 1 at one location, right? This is your, let me call this Y, Y1 through Yn, right? This is your desired output, and your cross entropy loss was minus summation di log yi, which is this term times log of this plus this term times log of this. You sum over the lot. There's the minus outside. And all the zero products go away. And so the only thing that remains is target, right? The negative of the log of the probability of the specific symbol that you want. Everything else goes away, correct? And this we are going to use repeatedly again and the rest of the lecture. So this divergence is the negative of the summation over all time of the log of the probability assigned to the correct symbol at time t, where the correct symbol is read from this time-aligned sequence, where we took the order-aligned sequence with the timestamps, right? Because we are assuming that we were told exactly at what time each symbol was produced, and then we just repeated those, right, to fill in the holes. So we're going to assume that the target sequence is this time-aligned sequence with the time synchronous aligned sequence, right? And the divergence is the sum over all time of the negative of the log of the probability assigned to the target symbol at each time. Okay? So again, have this burned in your mind. So when I compute the derivative, remember when we are doing a performing back propagation, we are computing the derivative of the divergence with respect to the output of the network at each time, right? So although the divergence itself is a summation over all time, the derivative for at any single time only needs to consider the local divergence, because the rest of the divergences are not a function of the output at that time. So that's going to be the derivative of the divergence with respect to any yt, which is the entire vector of probabilities, is going to be, since the divergence only has one term included, which is the log of the target probability of the target symbol, right? This derivative is going to be 0 everywhere except this one place, where it's going to be the derivative of negative of the derivative of the log of the probability, which is just minus 1 over the log probability, right? Again, nothing fancy. It's very simple. But then this keeps getting more complex. Stop me at any time, okay? And if you need a break, I'll give you a break. Here is the actual problem. If somebody were to provide you training data, they are only going to provide you the input of the kind that they really want as a response from the network, right? So they're going to give you the speech recording and say, this is the recording, hello world. Nobody's going to tell you, here's where the word hello ended, here's where the word world ended. That information is going to be missing. So in this case, how do you compute the divergence, right? Can anybody give me a solution as to how? I know that if somebody were to give me the exact times for every symbol, then I can compute a divergence. This we've solved, right? But if I were not to give you this information, then Derek, can you give me a guess, some random suggestion as to how I could go around this?
You can do something like a machine translation where you decode it at the end. So it produces a sequence of outputs at the end. Just like machine translation, the same model. So you basically you can calculate the divergence of individual data because everything comes together at the end.
I think you're jumping a few steps in this. Yes. But anybody else want to? He's right. I know what he's trying to say, but I don't think the rest of you made sense of that yet. So can somebody else, Ramil, how would you do this? Using only the information that you know so far. You're not allowed to jump ahead.
Then we take the whole sequence that we have outputted till now
He's sort of talking outside the scope of everything that we've covered, right? So, you want to take a guess? And if the answer is very simple, right? I can try to guess the times. Can I not? What is the information that's missing? Exactly at what time each symbol was being produced. So here, in this case, I told you that B was produced at time 2, E was produced, the word here is beefy, right? E was produced at time 4. Again, fur was produced at time 6, and E was produced at time 9. So the information that's missing is this information, exactly at what time each symbol was produced, right? I can try to guess it. Make sense? Right? So here's what I can do. I can start off by initially assigning some random timestamp to each of these guys. And now I have a time-aligned version. I can train a model using these initial guesses. And then once I've trained a model, I already have a model. If I have a model, I can go back and redetermine when the symbols must have been output, right? And then I have a new guess. And so then I can use the new guess of the time alignment and then retrain my model. Did I lose you? Does that make sense? Okay. Right? So basically, and how do you actually find the alignment? That is the key piece I left out of this, right? I've given you the symbol sequence. I've given you a model. How do I find out using the symbol sequence and the model exactly where each symbol was output? This is the piece that's missing, correct? So here is the problem again. You are given a compressed symbol sequence, which is the order aligned, but not the time aligned symbol sequence. And from this order aligned compressed symbol sequence, you're trying to produce the time aligned symbol sequence, right? So that you can find, which basically tells you where each symbol ended. So given a sequence of symbols S0 through Sk minus 1, you want to repeat each of these guys the appropriate number of times to fill up the entire time, right? So here, if you're just given beefy, you want to say that B repeats twice, E repeats 3 times, fur repeats 4 times, and then the final E is just once. This is the information that's missing. Make sense to everybody? Yes.
In practice, when you're given speech, isn't there a change in the amplitude when there's words? Couldn't you use that as a preliminary for the different words?
Not necessarily. Can you find out exactly where each word I've ended in the particular sentence that I'm speaking right now?
Okay.
Right. Right. You can't, right? It's not easy. So you're assuming that I'm pausing between. No, I never speak that way, right? So, and so you want to find an end-length expansion obtained by repeating the symbols so that the outcome is an alignment. Basically, you want to start off with ABC, and then you want to find out how to repeat each of these guys so that they fill up the time, which basically gives you an alignment of the symbols ABC against the input. Again, you understand the notion of an alignment over here, right, Michael? Yeah, okay. So what is the simplest way of doing it? Now I can just go ahead and decode. Remember, I already know how to decode stuff. So I could just train my model. I've initially generated an initial alignment of my symbols to my input. And then I can just use the initial alignment and train up a model. And then once I train up the model, I can run that model on my training data, on my training instances. Because remember, I'm trying to re-estimate the alignment for my training instances, right? So I could take some training instance and out pops a sequence of probability distributions, basically a probability matrix. I could pick the most likely symbol at each time. Will this work?
How do we know that it converges?
But that it converges is a different issue, right? But just finding the most likely thing, will this work?
What do you mean will it work? What is the end goal?
I'm trying to align the compressed symbol sequence. Remember, here is the process. I gave you a symbol sequence. What was missing was finding the exact times at which each symbol had to be output. So I started off by guessing these times. I trained a model, and then using that model, I reprocessed the input, and I got a sequence of probability distributions. From this, I want to go back and re-estimate the time alignment. If I just pick the most likely symbol, will it give me that? Johnny?
Symbols or number of symbols might be different.
It's not just the number of symbols. And here I want to, you're right? I want to get beefy, right? But the probability distribution is over all possible phonemes, all possible symbols. My initial model is going to be pretty crappy. The most likely symbol at each time can be anything. There's no guarantee. This is simply not the word beefy, right? I'm not aligning the input. I'm producing some completely random garbage. The output symbols are not the symbols that I want. Make sense, right? How would I solve this? Michael. Yes. Go ahead, Ram.
Okay. So we restrict the space to only those symbols.
So I can just block out everything that's not beefy, right? If I block everything out that's not beefy out, then I'm literally just sort of pulling out those 3 rows which correspond to B, E, and F, and now I have a restricted table. Those are the probabilities I'm going to use. And now, if I just pick the most likely entry in every column, am I going to get the right answer? Why not? I can get something like that, which could be completely off, right? Beef B, beef B. Just restricting the lines is not enough, right? What more could I do? So how would I implement that? Pardon me? No, but give me a process, right? The process is very straightforward. It's very algorithmic. I want to make sure that what comes out is an alignment of B phi, right? How would I do this? Here's what I can do.
We do basic sequence matching kind of thing, like for example, we get one set of probabilities.
It's getting too complex, right? So here is the simple answer. I want B phi, right? I'm going to pull out the B row and stick it on top. I'm going to pull out the E row and stick it next. I'm going to pull out the F row and make it the 3rd row here. And I'm going to pull out the E row a second time because B phi occurred twice and make it the 4th row. So now I'm creating this modified table where I have one row corresponding to each symbol in my compressed sequence. Make sense to you, right? The process that I'm following over here, right? Make sense? Okay. And now observe that if a symbol occurs multiple times, we repeat the row in the appropriate location. So, for example, E in B phi, E occurs twice, right? The model has assigned a probability to E at each time. I'm going to take this row and stick it immediately below B. I'm also going to stick it again below F. So the E has repeated. See what I've done, right? Now, why am I doing this? This eliminated my problem, okay? Because now I'm going to use this. So here is the little pseudocode for composing the graph. I'm going through my compressed sequence, which has n symbols. I'm pulling out the row corresponding to that symbol and sticking it below the previous row. So the first time I pull out the B row, then I pull out the E row, then the F row, and the E row again. I stack them together, right? So why would I do this? Here's why. Now I have this reduced table, and I'm going to assume that this is sort of 41 slides. I have 202. This class is going to last for a long time. Now, this is this table, I can walk through the table, right? Instead of just randomly picking a symbol, from every column, I'm going to impose an additional constraint. I'm going to say that I want to pick entries from this table such that the sequence of entries forms a path that goes from the top left to the bottom right. So this guarantees that the first symbol is B, the last symbol is E. I'm going to impose additional rows that from any location you can either move sideways or you can move one step down, but you cannot move two steps down. Right? So if I do that, then basically what you're really doing is ensuring that the sequence that you get is an expansion of the target sequence, B phi in this case. So if you want to visualize it better, you can think of it as composing this graph from each. Yes, Kiran?
Couldn't you also do this with stack, where you pop, where you push onto the stack in a particular order if need be, you push on twice, and you only pop off once you switch from like.
It's just a different way of implementing essentially the same idea, right?
It is great.
Yeah. So here's what we're really doing. You're composing a graph from this table, right? You're saying that from each location, you can either take one step right or one step down, right? And then this is the resulting graph. For each node in the graph, to each node in the graph, I'm assigning the probability of the corresponding symbol. Every edge in the graph has a score of 1, right? And now if I draw any path through this graph, that path is going to have to start from here, and you're going to walk through this over the edges, and you're going to end up over here. And you have a guarantee that regardless of the path you take, this is going to represent the sequence B phi. Right? And now what is the problem? I just have to find the path that has the highest probability. Right? And that's easy. Now what is the probability of a path? So consider any given path. The probability of any path is simply the product of the probabilities of the symbols on the path, of the nodes on the path, right? That's about it. And so I can compute the probability of any path all the way to the end, and I want to pick the probability of the path which is most probable. Now, if you do this naively, then you'd be enumerating every path through the graph, computing its probability, and then selecting the most probable one. So that's going to be exponentially expensive. But then you're all, most of you are computer scientists, many more of you are electrical engineers, you know how to solve this problem. The Viterbi decoding, right? Dynamic programming, right? So, yes or no? So, well, I'll go through this anyways, right? So, this is a typical path, and this is a typical end-to-end path. There are an exponential number of such paths. You want to pick the path with the highest probability, right? And you can find the most probable path from source to sink using pretty much any dynamic programming algorithm. There are several of these. The most popular one is the Viterbi algorithm. So the Viterbi algorithm is going to look something like this. You just observe that the best path, now consider this node, right? That node has only two parents. There are only two places from which you can come to this node. You can come to this red node either from this blue node or from this green node, right? So the best path to the red node must either be, this guy going to this blue node and coming down, or this guy going to this green node and coming down. So the best path to the red node must be an extension of the best path to the blue node, or an extension of the best path to the red node, right? Because you don't have deeper dependencies in the model. So, make sense to everyone? Right? There are only two ways of arriving at this guy. So, a path that ends here must be either an extension of a path that ends at the blue node, or an extension of the path that ends at the green node, right? So, I can write that like so. I can say the best path from here to here is either the best path from here to here and an extension to this guy, or the best path from here to here and an extension to this guy. Right. Now there's an implicit assumption over here that extending this path, the score of this node doesn't change based on which path you take to arrive over there, but that's true in this case, right? So that means that if I want to find the best path to this guy, all I've got to do is to find the best parent for this guy and extend it by one step, right? Whereby the best parent, I'm going to say the parent for whom the best path score was highest, right? Make sense to everybody, right? So you can implement it algorithmically like so. You can dynamically track the best path and the score of the best path from the source to every node in the graph. At each node, you're going to keep track of the best incoming parent and the score of the best path to that node. And then eventually you will use this to compute the best path from the source to the sink. So instead of just having this in words, let's actually look at it as an algorithm. Some notation. So observe the Y's in each box. Now the target sequence has, in this example, 4 symbols, right? Beefy. More typically, I can say the target sequence is S0, S1, S2, S3, right? So in this case, S0 is B, S1 and S3 are both E, S2 is F, correct? And so this symbol is really a generalization of Y subscript T superscript SR, which is to say the probability assigned to the rth symbol in the compressed sequence at time t, right? The explicit examples should make it easier to understand. And now, here's what we will do, right? I have this, I'm going to compose this graph first. And then once I compose this graph, what is the best parent of this guy? This guy has no parent, right? So I'm going to say the best parent is a null. What is the best path score to this guy? The best path is the node itself. So the best path score is simply the score to the node, right? And what about these guys? You are not allowed to start at those nodes, right? The first node must represent the phoneme B in this case. Otherwise, you'll be losing the first phoneme. So I'm going to be assigning an initial score of best path score of -infinity. They're really, really, really bad. Okay? Subsequently, here's all I do. I'm going to go through these one step at a time. For the first symbol, it's a special case. The first symbol has only one parent, right? So the best parent to this one is going to be just 0, correct? And the score of this guy is going to be the score of this time, the probability of this node times the probability of this node. I just multiply the two probabilities. And then for the subsequent nodes, like say this one has 2 parents. I'm going to find out which is the best parent. If this scores higher than this one, then the best parent is this one, otherwise it's this one. In this case, clearly, the first guy is the best parent because the rest of them have a score of -infinity, right? And so I will find the best parent and store the identity of the best parent in the table for this guy, right? And the best path score is going to be the best path score of the best parent times the score of the current of this node. So I can do this, I can scroll through this column top to bottom and perform this computation, right? And the computation is very simple. The logic is fairly straightforward. Because I already have computed the scores for time 0, I can now compute the scores for time 1. I can use the scores at time 1 to compute the scores for time 2, right? Again, at each time, I'm going to be selecting the best parent for each guy, and then, for instance, for this one, I'll be looking at which is the best parent, and retain a pointer to just the best parent and compute the corresponding score, right? And I'd scroll through the entire column one at a time to do this for every node. And I can fill this up column by column all the way till the end. At each step, for each node, you find the best parent, store the identity of the best parent, and then compute the best path score, which is the probability of the score assigned to the best parent times the probability of the current node, right? And so doing, what you have done in the process is to compute the best path score from the source to every node in the graph. Not only that, for every node, you also now know from where you must have come on the best path, right? At this point, you also know that the final node must be this point, right? So you know its parent, and you know its parent's parent, you know the parent's parent, that one's parent. You can trace these parents backwards, just walking backwards through the best parents table till you find the realigned sequence, right? And now you have a new alignment. And you can show that this will actually improve in the right conditions, that this will always improve the your loss as you define it, or the probability, okay? So here is the newly aligned sequence, right? It's B, B, E, F, E, 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 E. And now that so this is the entire Viterbi algorithm over here. Here in the first step, you're creating the output table, which is to say you're pulling out the rows corresponding to each symbol in your symbol sequence and creating this new table, right? And then in this portion, you initialize the first column, making sure that only the top left corner of the table has a valid probability. The rest of them in the first column have scores of -infinity. And then you go through the rest of the table, one time step at a time. And for each node, you find the best parent and then find the best path score to the node, which is obtained by extending the best parent, right? Now this code is somewhat wasteful in the sense that I'm pulling out the rows and creating a separate table and then only computing things from the separate table. But then if you actually look at how the score is extended, you're saying that at each time you're multiplying the score in any node, which is STI, and this guy just says that STI is simply going to be YT S of I, right? So I can take this term and plug it in right here, which means that this entire computation can be done without actually creating this extended table. Now, it's easier to look at this from a computational perspective than try to draw more complex graphs, right? Visualizing it the way I drew it makes the whole thing much more explicit, right? So, but you can go back. When you implement it for your homework, this is what you will be doing. Now, so you've assumed that from the first model, you have managed to find an alignment. And now you can use this alignment. This is the new alignment. You can use this alignment and go back and train your model, right? And once you've trained your model, you have a new model. You can use it and go back and find yet another alignment because hopefully your model is better, right? And you can keep repeating the process. So, of course, when you're trying to optimize for this alignment, your divergence is computed with respect to this new alignment. The derivatives are also computed with respect to the new alignment. And that's what you'll be minimizing. So here is the overall process. You'd initialize some alignments, train the model with the given alignments. Using the model, you'd go back and find the best alignment for every training instance. Then you can go back and retrain your models using these new alignments and repeat the process. And there are a couple of different ways of doing it. Once you've trained a new model, you can go back and find the best alignments for your entire training set and then use the new alignments to update your model. Or you can do this incrementally as you would in SGD. Every time you process an instance, you find the alignment, update your model, and then use the updated model to go on to the next instance. So there are different ways of doing it, but the basic idea remains the same, right? Questions?
I don't really understand the first.
So I have a collection of, so the first one is, I have a collection of training instances, right? T1, T2, T3. I use my model to find the alignment for each one. And then after having found the collection of alignments, I can go ahead and train my model, right? Or, which means that I'm not updating my model until I've computed the alignments for all of my training instances, right? In the second case, I compute an alignment and update it immediately update the model, right? So this technique would work, but there's a problem with it. Unless you have tons of data and tons of computation, it tends to be very prone to local minimum because you're very heavily dependent on this arbitrary initial alignment that you chose. If that happens to be bad, then with very high probability, you're going to end up in some crappy local minimum from which you are never going to escape, right? So why was this happening? This happens because every time at each step, you're using the current model to choose an alignment. And then you're using that alignment to train your model. What if I don't choose a specific alignment? What exactly do I even mean by this statement? So here's what we are doing. You had this entire graph, correct? From the graph, you chose one alignment, which was the most likely alignment. And then you use that most likely alignment to train your model, right? And this most likely alignment can be way off, particularly when the model is poorly initialized, right? But then, here's what you're really doing, right? This graph, with all of its nodes and all of its probabilities, actually represents a probability distribution over alignments. Does that make sense to you guys, right? Every single path through the graph has a probability, right? So every single path through the graph, so if this is not very clear, so, okay guys, I'll give you a break in 5 minutes and then you're going to come back and it's going to be a long lecture, but I want to finish this topic today, all right? So here's what happens. Consider this very simple graph. So let's say all I have is this graph, okay? What do I do? Something is funny. This should have been here. Right. Suppose this is my graph. Then in this graph, I have many different paths, right? So I have this path. I'll call this P1, and this has a probability P of P1, correct? This path is a second path, which is some other probability path, which has a probability P of P2. This path is a third path, right? And this has a probability P of P3. So I can go through all of my paths, and every path has a probability. So what the graph really represents is a probability distribution over paths. That makes sense to you guys? Right? And when we chose a path, what were we doing? We were doing a maximum a posteriori selection. We were picking the one path that had the highest probability. Right? Now, instead of picking just the most likely path, a better thing to do is to take an expectation over all paths. Right? Take an average over all paths, which is to say I take an average over all alignments. Does that make sense to everybody? Michael? So if I normalize by the sum of the entire graph, it will be 1. Right? So you're basically computing a probability distribution given that it must come from this graph. Each path has a probability, and you're basically selecting the most likely one. Correct? So instead of picking just the most likely one, I can do something nicer. I can take the expected divergence over all paths, which is to say that I'm going to compute the divergence for this path and multiply it by this probability, right? I'm going to compute the divergence for this path and multiply it by this probability. I'm going to compute the divergence for this path multiplied by this probability, and so on. And I'm going to sum over the entire lot. Right? I'm computing the expected divergence over all possible alignments of the input to the symbol sequence. That make sense? right? And that I can do like so, right? This is the expectation over all possible alignments of the divergence of the alignment of the divergence computed for that alignment, correct? But then what was the divergence computed for any alignment? Every alignment assigned a particular symbol at each time, correct? And so the divergence for any given alignment was simply the negative, the sum over all time of the negative of the log of the probability assigned, of probability of the symbol assigned to that time. That makes sense? No? Okay. Let me draw that again. Maybe this. So I have all of these inputs. X1, let me give you an example, X1, X2, X3, X4. And maybe I have only 3 symbols, right? So if my alignment is this, A, B, B, C, then the divergence was going to be, so it's A, B, C, right? The sum of the negative log probability of this guy plus the negative log probability of this guy plus the negative log probability of this guy plus the negative log probability of this guy, right? So for any given alignment, this sum was the divergence. If I had a different alignment, which was like A, B, C, in that case, the divergence is going to be minus of the log of this probability, which corresponds to A, plus minus of this log probability, right? Plus the negative log probability of this guy, plus the negative log probability of this guy. So every single alignment comes up with a different divergence, and the divergence is simply the sum of the logs of the probabilities assigned to the symbols along the sequence, correct? So that means the divergence is this term here, which is the expectation of minus of sum of the log probabilities assigned to all the symbols along the sequence, right? The expectation is a linear operator. I can move this expectation in, and that's going to be the negative of the sum over all time of the expectation of the log probability of the symbol, right? Which is, and what is the expectation of the negative log probability of the symbol? You're saying, you're literally asking, if you're going over all of the symbols in this column, and you're saying, if this was the correct alignment over here, what is the divergence? That's going to be minus log y4b, right? But what is the probability that that is the correct symbol at that time? That's given by this guy, right? So what is the probability that this is the correct alignment over here times the divergence that you would get if this was the correct alignment, plus what is the probability that this was the correct alignment times the divergence that you would get if that were the correct alignment, plus, what is the probability that this guy is the correct alignment, the correct alignment of the input to the symbol sequence times the corresponding divergence, plus the same thing for the same one. So you see what I'm doing, right? So for each, in each column, you're looking at each guy and saying, what is the probability that this was in fact the correct alignment or the correct symbol that must be assigned to this input? You are multiplying the divergence that you would get if that were indeed the correct symbol by the probability that it was the correct symbol. And then you're summing over the entire column. And this you're summing across all time. Make sense? Right? So all of these terms are available except one, because the network has already computed all of these probabilities, right? What you don't have is this one term here, which is the probability of seeing the specific symbol at time t given the symbols that the symbol sequence, the alignment, is an expansion of this compressed sequence, right? And we need to be able to compute this.